section 3.4. I'm going to approach this a little bit differently, and we're going to do this a little bit more conversationally maybe than we had done in the past. I'm going to go a little bit off book in terms of the notes here. So this is just kind of like me doing some examples and talking through things. We're going to kind of get into it, okay? So I'm not necessarily going to use the 3.4 chain rule notes that are in OneNote. We may circle back and do some of that content in there, but I'm going to start here instead because it feels like I haven't been getting as much out of the lecture as I'd like, and I'm going to try something a little bit different. Okay? That's not your fault. It just, sometimes something's not working, and rather than keep pounding that particular nail, let's try different. You know what I'm saying? So what we're going to talk about today is how to handle when I have a composition of two functions and I want to take the derivative. So you guys remember composition from Algebra 2 and pre-calculus, like f of g of x, where you have like an outer function, that's your f of x, and an inner function, that's your g of x, where you have like one function plugged into another, right? So just to start, I want to go through and do some examples of just identifying what is the outer and inner function for some of these compositions. Everybody okay with that plan? So let's just kind of run through that and make sure that we feel good about being able to kind of pull that data from looking at a function, because if you can't do that, everything afterwards is going to be a moot point, because this is a skill we have to have in order to differentiate things in that situation. Okay? So if we look at the function y equals quantity x plus 1 to the fifth, did you guys see a composition there? If you look at that, does that look like a composition? So it's one function plugged into another. So it's like an f of g of x. Okay? So x to the fifth is it the inner or the outer? The outer. And what's plugged into x to the fifth? X plus 1. Brooks.
So I know it's pretty obvious what is the inner, what's the outer. But with these, isn't it like the inner and outer, it could have like different possibilities. But it could be usually like it could be this, but it's even though it's like it's obviously this, like yeah, you're not wrong, it's this.
Yes, so there might be more than one option. For the most part, though, it'll be pretty obvious of what you should do. Now, obviously, like all problems like this, you could pick the outer function to just be x and the inner function to be the function, but that's not getting us anywhere.
Yeah.
Well, you'll see when we come to like how we do the derivative, why that's not going to get you anywhere. But for the most part, it'll just be pretty obvious, and there's just kind of one answer that you want. But sure, to some extent, there's multiples. All right, let's look at the next one. Sine of e to the x. The outer function is? And the inner function is? Okay. Does this feel pretty natural to you guys? Yeah? Okay. Let's look at this next one. 2 sine squared x minus 3 sine x plus 5.
Is the outer 2x squared plus 3x plus 5?
That is correct. And the inner function then would be sine x, right? Okay. Does everybody kind of see it now? A little bit harder to see this one. But in terms of, from a differentiation standpoint, do we know how to do the derivative of 5?
Zero.
Do we know how to do the derivative of 3 sine x? 3 cosine x, right? Do I know how to do the derivative of 2 sine squared x? No, right? That's the piece that we don't know how to do yet. So really, in terms of a composition, that's the only piece that I really care about. Because these pieces, I know how to differentiate already. What's the composition going if I just look at 2 sine squared x?
Isn't science going like
What's that, Matthew? Oh, no. What looks like the outer function? 2x squared. Uh-huh. And what's the inner function then? Sine x. You guys see that?
Yeah.
It's okay still? Lucia.
So if you're plugging in sine of x to x squared, why is it not formatted as like 2 sine of x squared? Why is the squared on the side?
So, because rather than writing this that ends up with like double parentheses, we've chosen to write it in the more convenient form of that. Those mean the same thing. though. Is that okay? So good question, right? That is what that means though.
Okay.
Keep in mind, what doesn't mean that? Right? What does 2 sine x to the negative 1 mean? 1 over sine x. What does sine to the negative 1x mean? That's sine inverse, right? That's a different function than 1 over sine x. So Lucy, that's the place where it kind of like, you really have to use that, putting the exponent there, notation, because it means different things.
Okay.
Is that okay?
Yeah.
Okay. Let's look at a couple more examples, and then we'll get into the calculus part, okay? If we look at this one, do you see a composition here? Where is the composition at? Just with this, right? You guys see that? What's the outer function? E to the x. And the inner function is 2x squared plus x. Does everybody feel still good? Not too far? Okay. How about this one? Last one.
What about the sine?
Well, it doesn't matter. There's no composition involved with it, right? There's nothing plugged into it. It's just like, you know, it's like some h of x times some k of x. And we know how to deal with the product of two functions if we take the derivative. So I don't care about this because I know how to deal with that. Does that make sense?
Yeah.
This is the thing, though, that up until this point, we don't know how to take the derivative of, right? I can do e to the x, and I can do 2x squared plus x, but I don't know how to do yet e to the 2x squared plus x, right? I can do this part, I can do that part. Don't know how to do that yet. But that's the idea, is we want to break these compositions apart into things that we know how to do the derivative. Does that feel okay? Last example, then we'll get to the calculus piece. We see a composition here, right? Okay. What's the outer? Okay. And the inner is?
X squared divided by 1 plus x.
You mean e to the x
Yeah.
squared over 1 plus e to the x. Okay. Do you notice anything else?
Then you can take the one of that one. That's what I'm talking about.
That is also a composition, right? What's the outer here? E to the x, and the inner is x squared. So we're going to have to now see that O I can have compositions, but I can also have compositions inside compositions, inside compositions. You can see this could get a little bit hairy here. Is everybody okay? All right. So let's get to how do I do the derivative of a composition. This rule is called the chain rule. And the chain rule just says that the derivative of a composition is the derivative of the outer, where the inner part stays the same, times the derivative of the inner part. Right? So that we take the derivative of the outside function with the old inner plugged in, times the derivative of the inner function. That's the chain rule. Okay? The rest of today, we're just going to grind through some examples of practicing this skill. Okay? Now I'm going to start out easy, where the problems are just chain rule problems that can be done with just the other derivative shortcuts we've learned without any of the product or quotient rules. And I'm going to start sprinkling in product and quotient rules, or multiple chain rules, or like multiple things. And we're just going to kind of keep, like, every so often, like, ticking up the complexity just one notch at a time. Everybody cool with the plan? So that's the entirety of today. It's just going to be practicing this skill, and then we're going to start blending in these old skills that we've learned into this new problem, or in with this new skill, and kind of see how they fit together. Pretty cool? All right. So if I look at this, sine of 2x, we see a composition. Okay, what is the outer function? Okay. And the inner function is 2x. So if I do the derivative, I'm going to take the derivative of the outer, which is cosine x. I'm going to have cosine of the inner times the derivative of the inner. And the derivative of the inner is 2, right? Go. Sarah. Yes. Unless it's in a multiple choice problem where you have to make, you have to match something down there. But yes, same standard is going to apply for the entirety of the course. So when the calculus is done, stop. Even if it's ducky looking, that's okay. Stop with the ducky thing. That's fine. Your college professor may not be so generous, but I will be. Brooks. Sure. All right. Next up. X to the 8th is the outer, good. And the inner. Okay. So the derivative of the outer is 8x to the 7. So my derivative is going to be 8 times the inner to the 7 times the derivative of the inner. What's the derivative of 2x to the 5th? Or 2x plus 5? 2. So this is just going to be 16 2x plus 5 to the 7. Is everybody okay then? Go! No, don't foil that out. Who wants to do that? No one. No. Look at how powerful this chain rule is, though. like 2x plus 5 to the 8th is something we could have done, right?
Yeah.
But to do it, what would we have to do? A terrible binomial expansion, or like just an insane level of foiling. How long would it take to have done that? Probably the better part of 15 or 20 minutes just to get it to a spot where we could differentiate it. That's something you could have done in your head with a little bit of practice. And it's already, and then it's back into a factored form, which is better than having it all foiled out and having to try to compact it back down. Duckarooskies. What a wonderful weapon. Right? This is so wonderful. I love this. Look at how happy I am. It's making my life easier. I love it when math makes my life easier. Couldn't we have started with this? No, but... All right. Do we see a composition?
Yeah.
Okay.
E to the x.
E to the x is the outer. Good. Good. 3x squared plus sine x is the inner.
Wait, are we almost done? There's another.
Time flies, right? Just a ripping and a roaring.
It's fast.
All right. Well, you're getting bonus learning here.
Extra learning time.
Yeah. So the derivative of the outside is e to the x. So when I start writing the derivative, I have this times the derivative of the inner, which is 6x plus cosine. Very good.
When you said sine of x or cosine of x, you can't simplify that. Just making sure.
Okay, so probably not unless you combine slight terms or something. Is everybody okay?
We wouldn't have to put because for the past ones, we put a derivative of the inner to the left of it, like in front of it.
Well, just because they were constants,
Okay,
right?
we don't have to do that.
No.
Because you can't.
Yeah, this, I mean, you could distribute this e through, but like it's not making it nicer than it is right now, right?
Yeah.
That's really as good as it's going to look. That's okay. Whether you want to put the 6x plus cosine x in front or back, who cares? I don't. You don't have to. Very good? Feel good so far? All right.
Clock's still going at it.
Difficulty notch increasing 1. You see 2 compositions. Good. What is the outer? Okay. And the inner is? And where's the second composition? Okay. The outer on that is? Cosine of x. And the inner is? Yep. Everybody okay? All right. So let's start. The derivative of the outside is cosine of the inside, the innermost function, so that's my g still, times the derivative of my inner function. Is everybody okay? So I took the outermost, took the derivative, all the insides come with it, times the derivative of all the insides. Well, how do I do the derivative of cosine x squared? I do another chain rule. So this is a chain rule inside of a chain rule, right? Yes?
Well, I was just going to say, so when you're trying to take the derivative of a composition like this, you just treat it as like a whole, but then have some examples.
Yeah.
Oh, so what?
It's another another chain rule, right?
Derivative of cosine.
The derivative of cosine is negative sine, right?
And it's squared, so
And the inside stays the same, times the derivative of the inside, which is just x squared now, because we're only looking at this derivative.
couldn't you say that cosine times cosine x squared is another composition?
But we're not taking the derivative of that. We already did it,
Oh.
right? There's no d dx in front of it. This part's not being differentiated. Already did that part. And at that point, you'd be done, right? Calculus is done. You don't have to clean that up. In fact, there's very little cleanup you can do other than like write negative 2x in front and then have the same crap behind it. Everybody okay? Let's do some more, right? Involve this kind of chain within a chain. We're building a link, like chain links, like we're building like a real chain, right? No.
You said negative 2x?
Yeah. Right?
Oh, I see.
So just pull all that stuff to the front and then just replace it. You know, like whatever, I can move those things. It's all multiplied together, so just let's move it along. So far, so good? Okay. Again, if I'm going too fast, if I do something you don't like, if you're not understanding, if you need to just hear it again, you need to stop and interrupt me. Don't get excited. Start going. If it's too fast, or I said something you missed, or you're just like, I don't get it, well, why did you do that? Just speak up, interrupt me. I promise you, if you're thinking this, there's multiple people in the same room thinking the exact same thing that are maybe just too chicken to speak up. Don't be a chicken, right? Be the egg.
Okay.
All right.
It's already not a lot.
It's really going. All right. Next problem. What do you see?
Composition.
Square root of x.
We see a composition within inside of a composition. The outermost is the square root of x.
Inner is cosecant. And that's another composition.
Correct.
Oh. And then it's cosecant to the x. And then e dx.
Good. You got to pass, right? Everybody so far so good. Looking okay? We see the compositions inside of compositions. Again, is this step that I'm writing down necessary? No, but where you're starting at, quite helpful, right? As you get more experience and you get some mastery and end up practicing and like get good at this, you don't have to write this, right? I don't have to write this when I do it, but you should at the start, right? Really helps so you don't have to hold the whole thing in your head. Once you get comfortable with the process, it's easy to hold it and do these linked in one line if you need to, but like, don't start there, okay? All right. So the derivative of the outermost is?
Half x.
Half x 1/4.
To the negative 1/2,
Oh yeah.
right? Because we subtract 1 from the exponent.
Okay.
So it's 1/2 CSC e to the x to the negative 1/2 times the derivative of cosecant e to the x, which we can't do directly, but it's a composition, so we do another chain rule. Okay. So this stuff just copies down. The derivative of cosecant is I think it's negative cosecant times cotangent. Let's double check.
That's just the derivative of cosecant.
Negative cosecant times cotangent.
And these are what we're supposed to memorize.
You do need to memorize this. 100%. The way I remember it is, this has got a sign in the denominator. That one has a sign in the denominator. The two with signs in the denominator stay together. I don't know if that helps at all, but that's the way I think about it. Go back to this. So we're going to have negative cosecant e to the x times cotangent e to the x times the derivative of e to the x. Ava, you said what? Where did I lose you at?
I just feel like it's really long.
Yeah, no, it's gonna. Like, you should see some of the ones I've made up for this worksheet that I'm gonna give you guys later this week.
So you're plugging e to the x to both of the x's?
Right. So this is the derivative of this is negative cosecant x cotangent x. So when I have the composition, the inner goes into both of them, right?
Yeah.
You see that? Why I chose that particular trig one because that's not, until you see that detail, you wouldn't think to do that. Or you'd be like, ooh, is that what I do? Not sure. Doesn't feel real natural. That is correct, though. That is what you want to do. Am I done yet?
No.
No. How do I know? I still have the d dx in there, right? What's the derivative of e to the x, though?
E to the x.
Okay, so that's...
Couldn't you do, since that's like 1.5 times, then it's like negative, I don't know, does that matter?
You do not need to worry about algebraic simplification unless it's like a multiple choice problem where you can't see what the which choice A, B, C, D is without doing algebra.
Okay.
So like if this is a free response question, you stop when the calculus is done. You don't have to clean it up. You don't have to do any algebraic simplification. That is okay. If I want to give you a problem where there's algebra, where I want you to do the algebraic simplification, just put in the multiple choice, where you can't get the right answer unless you've done enough algebra to see like, okay, that's going to be the one it is. Does that make sense?
Yeah.
Okay. And that's where the AP is going to test you also. Like on a free response question, you're done when the calculus is done. You don't have to simplify. And in fact, if you simplify and make a mistake there, you're going to lose the marks that you have gotten as you left it correct and unsimplified. So like, get out of the habit of doing that on a free response question. Just stop when you've done, when everything is done, stop. That goes for like a numeric calculation as well. Like if you're plugging numbers in, like you're doing a slope, just plug the numbers in and circle that as your slope. Don't simplify the numbers on an AP exam. Like if you make it like an arithmetic mistake, you'll be wrong. You just left it with the stuff plugged in. They'll give you a point. They'll give you the point. Does that make sense? Ava?
So just to make sure, you don't have to like change the negative 1/2 to like a square root on the bottom. Just leave it.
I'm good with you just leaving it.
Okay.
Yeah.
Yeah.
That's an algebraic simplification. Now, if it's a multiple choice question, that's probably the way it would be presented. But for this, I think we should do that. Does that feel good?
I wasn't sure if that's like not possible if it's like simplification. That makes sense.
That would be simplification. Yes. Sure. Yeah. And again, you can do all that stuff, and like when I assign the book problems, which I haven't done yet, even though some of us did them already, I think, which is okay. It's okay. I would encourage you when you're doing the book problems to look at the back of the book answer and see if you can do the simplification to get there, because it's not an unimportant skill to be able to do that simplification. That will be part of the AP exam. It'll just be as a multiple choice question. where it's like, okay, I got through the calculus. Now can I algebra this down to one of these choices? That is still an important skill to have, not something that I'm going to emphasize on the free response parts of the test because I don't want that to be like a time suck in that regard, because it's oftentimes like a black hole, especially if the problem is complex, right? And we'll look at some, like, that's not even that bad in terms of the simplification. But there's some like real doozies coming where the simplification be like, that's like going to be 20 minutes. You don't have 20 minutes to spend on this problem worrying about simplifying on the test. I don't want you to spend 20 minutes doing it. I want you to grind through the calculus and stop and move on. Okay? Is this helpful? You feel clear so far on what we're doing? Okay. Trying to just like limit the skill here to one day. All right. Difficulty, click one more. So this is another, what happened here that made this a higher difficulty? Frankie's got it. There's a product rule inside of my chain, inside of the composition. It's because she did the 3-4 homework already. That's how she knew. But yeah, you're dead on. Very good. So our outer function is cosine x. Our inner function is x e to the x. And that's a product rule. Because we have a function x times another function e to the x. That you can't combine those because one's polynomial and the other is exponential. So there's no like reconciling those into a single thing. So pretty cool. All right, we start the same way. The derivative of the outside is negative sine, and I'm going to say just stuff at this point when we're doing these chain rules. You just say like negative sine of stuff, and then times the derivative of the inside.
Plus.
So that's going to be my product rule. So I'm going to have x times the derivative of e to the x plus e to the x times the derivative of x.
Isn't the x e to the x? Oh no, you're not sure. You're not taking true.
That's good. And where the product rule came in and how I wrote it. And now I still have derivatives to do because I still have ddx's in here. Notice that I'm trying to only do one of these major rules in a step. Derivative of e to the x is just e to the x. Derivative of x is 1.
Do you have to have a little one there?
No. You don't have to write that times 1 in there. I'm writing it down because it's notes. So you can, if you go back and look at it and be like, what happened to the x? It's like, oh, differentiate that there. That's what it wants. And at that point, you could stop, right? There's more simplification you could do, but like, who gives a crap? I don't. Yeah, or darts. So far, so good. All right. What do you see here? And the chain. Yeah, very good, Ava. Which one should come first, the quotient or the chain? No. The quotient comes first because notice that the e to the x squared is inside of the quotient, right? The quotient isn't inside of the composition. So we always have to, order of operations, work from the outside in, right? So here the quotient is coming first before I have to differentiate the e to the x squared, right? You all see that? No, you're making faces like me.
So, so if it were, let's say it was all in parentheses, squared, then
the squared is the first chain, yes. So Noah's saying like, we had this, now it's a chain, inside of the chain is a quotient, inside of the quotient is another chain. Yeah. Will you get something like that? You betcha. Just not quite. Lucia's making faces like, I don't want that, Mr. Gulick, though. Why do I have to? I don't know what to tell you. Sometimes we gotta do stuff we don't want to do. All right. Quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. Okay. So I'm gonna, because of the nature of the quotient rule, how much writing is involved here, I'm gonna just do the derivatives for these parts just above it. Is that okay? Just to save myself some writing. The derivative of 1 plus e to the x is? So I'll write 0 plus so everybody can see the derivative happening. Do you have to write the 0 plus? No, of course not. Okay. Next one.
E to that's that.
That is. It's okay. There's a composition in there.
Is when doing the derivative of composition, the first part is almost just like.
It's the derivative of the outside times the derivative of the inside.
Oh, never mind. The derivative of the outside is just e.
Exactly. So everybody so far so good?
Yeah.
But isn't the outside e to the x and the inside is the x squared?
Uh-huh. So it's the derivative of e to the stuff. The derivative of e to the stuff is e to the stuff. That's the derivative of the outside. Right? So like, go back to the formula. Right? It's the derivative of the outside with the inside plugged in. Times the derivative of the inside. Which is what we had here, right? That's the derivative of the outside, e to the x, with the inside, the x squared plugged back. You see it? Okay. And then if I do that, I have negative e to the x squared times 2x. So if I wanted to write my final answer now, so again, if you're going to show your work this way, that's fine, but like collect me a final answer. Even if you don't want to do any more simplifying, that's fine, but like collect it together if you're going to do this writing, saving notation that I've done here. It's totally fine to do that, but like collect me a final answer. Just so it's absolutely clear to me as the grader, like what is your final? You know what I mean? And again, you don't have to do any simplification there. Very good.
How did you go from the last line of like the 0 minus e to the x squared to the x squared? How did you go from there to like the last?
So did this?
No. From below that.
Talking about this?
Yeah, there.
2x times negative, and then e to the x squared.
Oh, I just got confused because you wrote it above.
Yeah, I just kept going up.
Okay.
It kept going up.
So what is the outer and the inner composition?
Well, the composition is just here.
Oh, okay.
So the outer was e to the x and the inner is x squared. But the composition was inside the quotient, rather than the quotient being inside the composition. Right? This is the first time we've seen a composition inside like a quotient or a product or whatever. So they can happen both ways. That's the point of me, like continuing to kind of click up the difficulty here and showing you lots of these examples of like, oh, it can happen this way. Oh, it can happen that way. Oh, it can happen, and you're just basically always working from the outside in. But it's important that you're able to look at the problem initially and be like, okay, I see it, and I see the sequence in which they're going to happen. That helps enormously if you can take 10 seconds at the beginning and kind of pick that out. What are we doing? Still okay? No? Yeah, look at this fun guy. All right. Tell me what you see.
Square root of x.
So let's talk just how many chains, quotients, products, etc. What do we see in here?
We have one product, two quotients, and a few.
How many compositions? 3. Because of the square root, yes. So I see, which one happens first? The square root is the outermost of the function. What's going to happen after that?
Product.
The product rule is correct. After the product rule is going to be the chains. And the last thing is going to be the quotients. Because those are the innermost parts, right? It's going to be a big boy, yeah. So this would be more difficult than something I would give you on a quiz or a test, because this is going to be like, it's going to be like 15 or 20 minutes here for us to do this together, just because of the writing involved and like wanting to walk through this slowly and be careful about it, okay? Because there's a lot going on, right? There's 6 derivative rules going on, right? 3 chains, 2 quotients, and a product. That's 6 derivative rules. I'm going to take some lines to do this, which means I'm going to have a lot of rewriting, and that just takes time. But I want to make sure I'm going slow and careful. I'm just going to do like 1 rule a line so that I don't get too bogged down. All right. We correctly identified the outermost function as the square root, right? What's the derivative of the square root of x?
1/2 times negative 1/4.
1/2 to the negative 1.
Oh, yeah.
1/2 stuff.
1/2.
Everybody, so far so good. I'm going to pause in between these and give you a chance to process what just happened, because this is a rather long and complicated example. But if you can see your way through this, it's like, okay, Mr. Kulik, like, it's not going to get much worse than this. If I can handle this, I can kind of handle anything you throw at me. All right. So this part now is locked and finished. Am I ever going to do anything with that again? In the interest of my own sanity, I'm just going to do like this. And I'm just going to remember that, like, when I copy down my final answer, I got to go all the way back up to step 1 to copy that part. But, like, I am uninterested in writing this over and over and over and over again. It just feels like it's an opportunity for me to miscopy something.
That's what dittos or whatever is, right? Like,
Yeah. So I'm just going to do, like, one of these guys. All right. So now I'm here. What do I have to do the derivative of this? Excellent. Product rule. So I have first part times the derivative of the second plus the second part times the derivative of the first. Zoom out a little bit. Sorry, it's getting small, but like, them's the breaks. You know, this is going to be a long problem. or wide problem. It's okay if you use more than one line in your paper. If you're a big writer, you might need 2 or maybe even 3 lines to write the final answer on this. As you see, it's going to get pretty wide. It's okay.
You could like ignore the blank part and just like
That's true. So I'll just do that. Make it smaller. All right. So now we have to worry about these 2 derivatives, right? How do I do the derivative of cosine of e to the x sine x?
it's change.
Very good. So that's going to be negative sine e to the x over sine x times the derivative of e to the x over sine x. It's less confusing, I feel like. And then I have plus cosine e to the x sine x. And then I have the derivative of sine is cosine insides times the derivative of the inside. Nope, quotient rule. I know, right? Yeah. Okay. So this guy's still coming down. Now I'm going to take this negative sign to the front just so I can drop a layer of parentheses there on that middle guy because it's getting a little like woozy. You guys see it, what I'm saying? Just going to move that to there just so I can drop a layer of parentheses. Now the derivative of e to the x over sine x, I need a quotient property. Oh my God. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. I'm just going to write that as sine squared x. Just, again, drop a layer of parentheses there. Is everybody okay there? Okay. So again, what we just did, that's that piece, right? Just trying to kind of keep our place. Sometimes the hardest part about this is just the transcription, right? Is like keeping track of where we are in the problem. So just recopy those 2 parts down. And then the derivative of x minus 1 over x plus 1 is a quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared.
Which one is this?
So we just had that part. But we're almost done, right? How many derivatives do we have left? We just have those 2 itty bitty guys left, right? I got just like this guy and that guy. So this can be my last line, so I'm going to write it all in now. So I'm going to go back and put this blank in. So far, so good. And I'm going to have this piece. And now in the interest of time, those guys both differentiate down to 1, right?
Which one?
Derivative of x minus 1, derivative of x plus 1.
Yeah.
So I have x plus 1 minus an x minus 1, so that's just going to be 2. There, the simplifying made sense to me. Is it like saved me some writing? Notice I didn't bother over here because it wasn't going to save me anything.
So just like as for big ones like that, as soon as all the derivatives and all the quotient properties and product properties,
As long as you have no more ddx's, you stop. Because look at that nightmare. So the moral of the story here is you're just peeling the onion, right? You do one major derivative rule a step. In this case, there were 6 major derivative rules you had to do, and a bunch of steps to kind of peel through. It's okay. Go slow. Be neat. Be organized. Take your time. Don't try to do too much in one step. All of the small intermediate steps where we had to do the derivative were all doable, right? It was just kind of not getting lost inside of this monstrous problem in the process. What was I, like 12 minutes on that? It was old-fashioned, like 15 or 20. What do you guys think on today?
It's like the steps for erasing stuff, just like when you do something like this. Really fast.
Yeah, so, and again, that is pretty typical at this level for the course. It's the individual, like, parts are not going to be difficult, but like keeping track of where you're at in the process and having enough concentration to like hold on to where have I gone and where do I still need to get to. That's the hard part. I don't have anything for you to work on for next time. Though next time you should expect, we will do a homework quiz, just using the rules from 3.1 through 3.3, not including today. Okay? So power, e to the x, product quotient, and trace. Okay? So like those 4 sets of rules. We'll start with that. We'll do a little bit more in 3.4. And then on Friday, I'm going to give you just like a big sheet of derivative practice problems, just like we did today.
So you don't have any homework today?
No homework tonight. I will assign a 3.4, but I don't need to. You don't need to start it today. If you're worrying about the 3.1 through 3.3 homework quiz, worry about that, right? But there will be time for 3.4. We'll do practice on it, I promise. If you're like, I need to practice it tonight, go for it. Do some practice on it. Don't worry about finishing. Man, so 3.3 or 3.1 through 3.3. So power rule, e to the x, product quotient, trace.
Should we memorize all the like things for next class for
The tricks? Yeah.
For the mini quiz?
Yeah.
Alright,
Yeah, for sure. Half your tricks memorized.
okay.
The sooner the better. You want those memorized so well that your children know them, right? That's the goal. I promise you. Like, you don't want to sit there and have to kill 2 minutes on a test going, the root of cosecant, is that negative or positive? I just gotta know. Be able to rip it out.
Loving God, thank you for being with us throughout this day. We are grateful for our school where we can learn, grow, and live our faith freely. Thank you for the teachers, classmates, and staff who help us become the people you call us to be. Thank you for our campus ministers and our student ministers for a beautiful adoration service today. Bless our families and keep us safe this evening. May we rest in your peace and rise tomorrow ready to serve you again. We ask this through Christ our Lord. One quick announcement in the high school, girls varsity swim practice is canceled for today. That's all for today, Narendra. Have a wonderful evening. God bless. Teachers will be dismissing students as you are ready.
I am ready.
Thank you.
Have a good day. What's up?
So for IBSL,